start recording.
Okay, welcome everyone back. Today we are very happy to have Pavel Etingof, who is going to tell us about Deligne categories and deformed double current algebras. Please take it away.
Okay, thank you very much. So can everybody hear me well?
Yes, I think so.
Okay. Yes. So so the first thing I want to talk about these doubly deformed current algebras. So I'll be talking about our joint work with my graduate student Daniel Kalinov and Eric Rains from Caltech. This is the paper, archive 2005, 13604. And so the first thing I want to talk about is doubly deformed current algebras, but before I define, so the doubly deformed current algebras, the deformed double current algebras are obtained as certain limits of Cherednik algebras of certain kinds. So let me talk about those first. So rational Cherednik algebras. For symmetric groups. So these are the following algebras. So this is algebra. Everything is going to be over complex numbers. I could work over other fields, but in a physics seminar, I will work over complex numbers. So so there is this very nice algebra, which I will denote by h k of n. So k is going to be a parameter, coupling constant. It will be related to the coupling constant in a quantum Calogero-Moser system. So this is generated by the symmetric group Sn, or permutations of n items, and also variables x1, xn, y1, yn, so generators. And the relations are the following. So first of all, symmetric group permutes xi and yi as usual. So if you conjugate xi by permutation sigma, it will go to x sigma of I, and it's the same for y. Also, x's commute with each other, xi, xj equals to yi, yj is 0. And the only interesting relation is, so let me, maybe I should call this htk, because it's going to have two parameters. So the third relation is the interesting one, and it's so yi commutator with xj equals to k times s ij. So this is the permutation of I and j, and then commutator of yi with xi equals to t delta ij minus k times the summation over j different from I Sij. So this algebra is important for many reasons. It arises a lot in representation theory, but also in mathematical physics. So the reason it arises in mathematical physics is because of connection to the quantum classical and quantum Calogero-Moser system. And the connection is the following. So it has a realization by so-called Dunkel operators.
Pasha,
Yes.
the last relation, is it?
There shouldn't be delta probably there. It's just there is no need for delta after t.
Oh, thank you. Yes, just t, yes.
Mm-hmm.
So there is a realization via Dunkel operators. This is the following. So it's action of this algebra on polynomials, well, maybe rational functions. But if you conjugate appropriately, it will preserve polynomials x1, xn, and xi act just by multiplication by xi, and Sij just act in the usual way by this Sij. And the interesting action is of yi, so they act by Dunkel operators, di, which is t times partial derivative di, plus k times the summation j different from I, 1 over xi minus xj times Sij. So these operators commute with each other, so the commutation relation is satisfied. Number 2, and also you can check that relations number 3 are satisfied, so it's a pretty easy calculation. And then one may consider so one may consider the operator sum over I over I squared, and we can call it H. And so this is going to be, so you can compute it. And let me restrict myself to t equals to 1, just for writing formulas, because you can rescale. So there is a scaling symmetry. So if you take tk, there is a scaling symmetry lambda t lambda k. So there is a simple isomorphism. You can rescale the variables so that you will get this symmetry. And then this t plays the role of the Planck's constant. And so the limit t goes to 0 is the classical limit. Semi-classical limit, and it's so in this limit, of course, you have to in order to get an interesting limit, you have to replace this in the classical limit by classical momentum operators. Okay, but let me consider the quantum case when since I can rescale, I lose nothing by setting t to 1, and then H is going to be the sum of yi squared. And then so I'm going to restrict it to invariant polynomials, invariant functions, symmetric functions. And then this turns out to be, then this is a differential operator, and this is nothing but the Hamiltonian of the quantum Calogero-Moser system, which is the Laplace operator minus k times k plus 1 times sum over I not equal to j, 1 over xi minus xj squared. So we have n Calogero-Moser particles on the line, which interact with the potential kk plus 1 over x squared. And so this is what it is. So delta is the summation of di squared. And this allows us to construct integrals of motion. quantum integrals of motion. So we can define Hm to be the sum over I, yi to the m, restricted to invariant functions. And then, so these operators, so Hm, it has symbol d1 to the m plus so on, plus dn to the m. But then there are some lower terms, and this H is commutative. And of course, H2 is just H. And H1 is just the translation, sum of d. And so this means that this is a quantum integrable system. And then one can study joint eigenfunctions of these operators. They're the multivariable Bessel functions, which are very interesting functions. I will not discuss them today, so I will explain how these Cherednik algebras can be, what happens to them when you take large n limit, or rather when you interpolate them to n being a non-integer. So any questions up to this point? Yeah, so far this is classical stuff, which was known like 30 years ago. So I'm just doing a review.
So there's a sort of toroidal version of this. I mean, the other Cherednik algebra, the non-rational one, right? Will
Exactly,
the story
yes, there
extend
is
to that as well?
Yeah, there is a toroidal version. So there is so this is called a rational Cherednik algebra because it involves these rational functions 1 over xi minus xj, so potential 1 over x squared. You can consider the trigonometric version where you will have 1 over sine squared.
Yeah.
And then you can also consider difference operator version with McDonald operators, and that's related to the toroidal algebra. Does it answer the question?
Yeah, no. So my question was, the story you will tell us about extending to large n. Would it hold also for this for the other versions of the algebras, or this is special for the rational one?
Yes, well, most of the things I will say will hold for other versions, but there is a special presentation that I will explain, which we only know in this rational setting.
Okay.
But this, I have to say that in physics literature, actually all versions appear, including this rational version.
Sure. Yeah. Yeah. I mean, I guess the toroidal one was specifically interesting because it answered as refined Chern-Simons theory, I guess. But and there,
yeah, so
the issue of large n is particularly interesting as well. So.
Right. So what I've said so far can be generalized to that setting. Okay, so let me now say that so this symmetrization procedure that I described here corresponds to some operation with these algebras, namely defining spherical subalgebra. Spherical subalgebra, and this really came from the theory of representations of p-adic groups, where they have spherical Hecke algebra. So spherical subalgebra is the following thing. So you have in the group algebra of symmetric group, you have this symmetrizing idempotent E, which is 1 over n factorial times sum over all elements. So this is the symmetrizer. And then you can, so this of course is an idempotent, so E squared equals to E. And then you can define the algebra E H K. So I will say that H1 K of n, I'm just going to call it HK of n. But we should remember that we can take classical limits, so of HTK of m, and then we will get H0k of n, which is a kind of classical algebra. And so, but in the quantum case, I have this EHKE, which is called the spherical subalgebra. Of HK of n. And this spherical subalgebra is it's a unit. It's not a unital subalgebra because its unit is not equal to 1, but its unit rather is this element E. So it has unit E. And its representation theory typically is the same as HK of n. So for generic K, so for K not equal to minus R over n, M, where M is an integer between 2 and n, and R is an integer between 1 and m minus 1, it is Morita equivalent to HK of n. So the module categories are equivalent. So category of modules M over HK of n goes to En over EHK. So there is a simple correspondence between modules. This functor exists, of course, also at the special values, but at those values, sometimes you can have a non-zero module M such that E of M is 0. And so this functor is not an equivalence between representations. So you can think of this algebra. Well, we know that so this E, H, K, and E is the algebra generated by polynomials and the Kalogero-Moser Hamiltonian H. And we can say that it contains all the higher integrals. Okay, so this is this spherical Cherenik algebra, and then one can do the following thing. So so we want to the limit when n goes to infinity, and or rather make n an arbitrary complex number, which is not necessarily an integer. And for this purpose, what you can do is you can consider the elements let me call them T, K, L, which is the summation over I, xi to the k times yi to the L. And I is going to be from 1 to n. So in particular, T00 is just n. And then let's say T10 is just the sum of xi. T01 is the sum of yi, which is sum of the derivatives di. And T02 is so I will actually times e on both sides. So this will be an element of this spherical subalgebra. Maybe I should not call this k because my parameter is k. So I'm going to call it m. So T02 is this Hamiltonian H, and so So you can think of this sitting inside the differential operators. So these are differential operators, if you like. And then you can look at the kind of algebra they generate. So okay, so we can take so these are of course algebraically dependent for every fixed n. So these are algebraically dependent. For every fixed n. Well, because there are infinitely many of them, but asymptotically they are independent. Which means that there will, if you have the fixed finite collection of these t's, then for large enough n, they are independent. And in fact, if you take a large n, any relation will have to have large degree and involve t's with large indices. So, and so in particular, this means that we can look at the elements z. Let's call it m. So suppose we have a function. So we have a function n. And this is a function from z plus cross z plus minus the origin. So it's basically all the points like this. And the function is with values in non-negative integers. So this is a collection of numbers n, k, oh, sorry, m, and ml. So this is the product of over m and l, t ml to the power n and l. And because we are in a non-commutative algebra, we really have to say in what order. So we choose some ordering. And then this is going to be called z sub n. And then you can try to multiply them. Zn times z, let's say p, is going to be the sum of some constants cn p q. So let me actually use capital N for the rank, which is consistent with physics notation. Capital N. So of h, k of capital N. So this means I want to make that complex number, and so then the sum will be until capital N. And so this is N. Okay, and so then I have this, these are going to be some functions of this N times Z. Q. So this is going to be some finite sum. And so, as I said, if I take n is very, so this function is takes only finitely many values, finitely many non-zero values. So this means that these products are finite. And so then if I multiply these things, if I take n very large, there is only one way to write this involving ZQs also with the bounded size of this cube. And these things are going to be polynomials in n. So one can show that these are polynomials in n. And of course, all of this is quite clumsy because we have to choose these orderings and so on. So it will be slightly nicer if you choose the kind of symmetrized expression. So instead of taking one product, you can take average of all possible orderings. And so there is a slightly nicer way to do this. So it's like when you quantize, for example, a polynomial of x and p, there are many different ways to do that. But what happens is in the algebra, so these polynomials of n are going to, of course, depend heavily on the way you do it, but the algebra you get will be independent of that. So, and there is a mathematical proof of this, which is based on another construction of this using the so-called alter product limits. It's a kind of language from maybe model theory to talk about such limits. There is also an elementary way to see it, but in any case, there is a way to see that that algebra will be independent. So we get an algebra, which I will call y k nu. And so where nu is this variable n, but viewed as a complex number. Because once I have such presentation, I no longer need n to be an integer, because n is no longer occurring as a index of summation, but only occurs analytically in the expression of these coefficients. And so that's that gives me some algebra. So, and one can, and so this is a deformation of the following. So if k equals 0, which means we don't have interaction of particles, so we have basically a free theory, then we get this y0 nu, and this y0 nu is simply the enveloping algebra of the Lie algebra of differential operators on the line. So we view this as a Lie algebra, modulo the relation that unit in this algebra, well, it's not the unit in the Lie algebra, sorry, well, this is associative algebra, what we view it as a Lie algebra, in particular, it has element 1, and so this 1 has to be equal to nu times the ordinary one. So in other words, it's a quotient by the ideal generated by the relation 1 minus nu. And so, so in other words, it has so this the algebra has basis x to the I times d to the g and j are in z plus cross z plus. And so this is this thing. And so this is deformation. So this is actually, so if you take, so this has a filtration and appropriate filtration. And if you take yz nu ger, this is going to be just polynomials in, so if I call this generator zij, then this will be polynomials in zij, where I and j are both non-negative, and I plus j is strictly positive. But so the corresponding quantum algebra depends on this nu. So it's a two-parameter family of algebras, and this is what is called doubly deformed double current algebra. For GL1. So there is also a version for GLN. So it's a deformation. So there is also a version for GLN. And to define this version, what we need to do is we need to take this H K of capital N, and we should tensor this with C n to the nth power. And then there is a symmetric group. I'm sorry, not with this, with matrices to the nth power. Matrices of size n to the nth power. And then, well, there is a symmetric group sitting here and also here. And then there is a diagonal map from the symmetric group to here. And then, so if you look at the group algebras, there is this co-product map. And then here there is this element E. So we should look at delta of E times HK of N matrices N of C to the N times delta of E, something like that. And so this is going to be a deformation. So this is going to be Y K mu of GLN. And so this is a YK nu of GL1. And so this is a deformation of the enveloping algebra of GLN of tensor product with differential operators of C modulo 1 equals to, which is Y0 0. So this Y K nu of GLN, so this is a doubly deformed double current algebra. And so this is a rational degeneration of the Youngian Y of GLN hat. So that's why I use the letter Y. So Youngian of GLN. So this is some kind of rational limit of Youngians, and it depends on two continuous parameters K and mu. So I will explain first some construction of the so there is a construction of this. So the construction that I gave is not very convenient because it doesn't give you a presentation of this thing, and also it doesn't allow you to easily study its representation. So it's a kind of a proof of concept, but it's not a very convenient. It's not a very convenient definition. Well, to some extent, you can turn it into something more convenient, which is using Deligne categories, which is what I explained. But you can also construct it by generators and relation. And this was done by Gui. but in a way, he has to require that n is at least 4. So it turns out that his method, which is based on things like Steinberg presentations of GLN, when you generate GLN out of upper and lower triangular matrices and write relations between them. So this method does not work for small n, in particular for n equals 1. So there are now other ways to do it, and Gui is working with his collaborators on writing up this theory for any n using a somewhat different approach. But in the definition that I gave, it doesn't really matter what this n is. So what I want to do now is I want to explain first some presentation of this algebra in the case of GL1, which is new and which is based on realizing differential operators on C equivariantly with respect to SL2 acting by quadratic Hamiltonians. And then I will explain how to apply Deligne categories to this story. So any questions up to this point?
Yeah, so this rational degeneration of Yangian, is that the relation between the two, is that supposed to be obvious? Is it and which rational degeneration? In my book, Yangian is already in some sense rational. So what are we doing?
No, so Yangian is rational, but so what is Yangian? So Yangian of GL and here is a deformation of the universal enveloping algebra of GLN hat of some variable, let's say y, but only positive power of y. So for any Lie algebra, Yangian of G, so Yangian of G, so if you take associated graded of Yangian of G and appropriate filtration, this is enveloping algebra of G of y, some variable y. And so, but this is what it is. So this is for zero central extension. This is enveloping algebra of GLN of T inverse and y. So this means that so this polynomial in T inverse and y is polynomials on C star cross C. So this one variable is trigonometric and the other is rational. Now this Yangian yk nu is that this degenerates to C. Does this answer your question? Other questions? Is it too fast what I'm or is it normal speed? Good. Okay. All right. So so now presentation. So SL2 equivariant presentation. Of yk nu of GL1. So let's just call it yk nu. So this presentation is the following. So first of all, well, I said that this is so the associated graded of this yk nu. So this is enveloping algebra of differential operators, but actually you can further grade it so that it will be the graded version of differential operators on the line, which means that classical limit. Classical limit is so it's the Poisson algebra. So C of x p with the Poisson bracket. So let me call this algebra P. So Lie algebra of Hamiltonians in the plane. That's a very simple Lie algebra to define. So there is a simple formula for the bracket. but it is kind of mysterious. For example, its cohomology, I think, is not very well understood, and so on. But so to present this algebra YKNU, we first consider presentation. So what's a presentation? Of this. And then we deform this presentation to show that there is essentially a unique way to deform it to preserve filtrations, and that will give us this Y. But the presentations that we will use are, so the physics literature, there is a number of ways to think about this algebra, going back to the work of Hikami and Vadati in the 1990s. But what I will consider is the SL2 equivariant presentation. So this means that, so this Lie algebra contains a copy of SL2. And it is generated by the quadratic Hamiltonians, p squared, xp, and x squared. So this is classical Hamiltonians. So this is rated, and then this can be written as a direct sum of representations of this Lie algebra. So I will write label representations by dimensions. So V1 plus V3 plus V5 plus V2, I'm sorry, plus V3 plus V4 plus so on. So this is the one-dimensional representation, the two-dimensional representation, this is the three-dimensional. So this is the Lie algebra itself, and then four-dimensional and so on. So if you draw it on checkered paper like this, is the basis of this algebra, like this. So this is like, for example, monomial x squared p cubed. Then you will get, so this is V1, and this is V2, this is V3, this is V4, and so on. And this is a grading, and the commutator is SL2 equivariant. But the question is, how can we generate? So, so this is this Lie algebra is generated by, so we have to put in these things up to V4. So V1, V2, V3, and V4. And so the most interesting part is V4, which is cubic Hamiltonians. And by taking brackets of cubic Hamiltonians, we can obtain Hamiltonians of any degree. And the question is what the relations are. So what are the relations? Well, of course, there are some obvious relations. Which are things like that. For example, V1 is just constant, so this is in the center, and then so V2 with V4 is in V3. So there are some obvious relations like that. So I'm not going to write them down, but and then there are also interesting relations. Which involve V4. So basically we have this subalgebra here, which starts from V4. So these are cubic and higher polynomials. So let me call this algebra N. So it's like plays the role of nilpotent subalgebra. So this is so we can, in some sense, think about this as follows. So there is a, so we can think of this as, so to speak, Cartan, even though it's not commutative. And then there is this n minus which is this. And so the interesting relations are for n. So presentation of n. So n is generated by V4. And what are the relations? And we can write down those relations equivariantly with respect to SL2. So this problem was studied by Fagin in the 80s. And then it was solved, published presentation is by Hidge, Ligen, Berg, and Post in 1991. And so the answer turns out to be quite simple. So, what kind of relations do we get? Well, first of all, let's look at the commutator V4 with itself. So this means we have a second exterior power of V4. So it means we commute two cubic Hamiltonians. And so, well, for SL2 representation, this is just a 6-dimensional representation, which is V1 plus V5. So trivial representation plus 5-dimensional representation. And then this trivial copy has to be cubed. So, so first relation, so let me call this phi1 and phi2. And then there is a relation which is phi1 equals. Then, okay, so that means that when we commute two cubic Hamiltonian, we are left with this V5, which is quartic Hamiltonian. So what happens if we commute them with cubic Hamiltonian? So V4 cross V5, well, we can decompose this. And so this is V2 plus V4 plus V6 and plus V8. So let me call them psi1, psi2, psi3, and psi4. And then it turns out that you have to kill, so here you kill this one, here you have to kill the first and the last. So those get killed. So the relation is that psi1 is 0 and psi4 is 0. And then there is a third. What happens when we commute V5 with itself? So wedge 2 of V5, which is the 4, well, which means that I commute two commutators. And so that wedge 4 of V5, well, it's V3 plus V7. And we need to kill this V3. So this is, let me call this chi1 and chi2. And so the relation that you need to put is chi1 equals to 0. And the theorem that they proved is that, so HP is that, that's it. So this Lie algebra, the Lie algebra of polynomial Hamiltonians is generated by V1, V2. Well, let's say greater or equal to 3. So that's the relevant part. So this is generated by V4 with these relations. So there are 4 relations. Phi1 equals 0, psi1 equals 0, psi4 equals 0, and chi1 equals 0. Okay, so this is a very nice theorem. And then what we will do is now we will deform these relations, and we will see that, well, one can show that there is essentially one way to deform them to obtain this y. Any questions up to this point? Okay, so so now so deformation. So first, so deformation can be, so the most general deformation. So this is a theorem that we prove that the most general deformation preserving appropriate filtrations. I will not detail this too much because I want to get to the Deligne categories, preserving filtrations. So I look at equivariant deformations under SL2, which preserve filtrations. And then, so what you will get, so first of all, so let's say, so we have this V0. And this is a one-dimensional space spanned by a central element, which is called K. And so you can deform the relation phi1 to say, instead of being 0, remember phi1 lives in the trivial representation of SL2. So it can be some constant C1 times K. Now, psi1 can also be deformed, and it can, so under appropriate normalization, so it turns out that the deformation constant is the same. They have to be deformed synchronously. So the parameter of deformation for the first relation and the second relation has to be the same, or they have to be proportional. So this lives in the two-dimensional representation, and so there is this V1, which lives also in the two-dimensional representation. So for appropriate normalization of this V1, the deformation of psi1 is by this constant. And then there is no way to deform psi4. So psi4 has to remain 0. And then you can deform chi1. And that's the most complicated thing. So chi1, as you remember, lives in the three-dimensional representation. So there are actually two ways to do this, and so there are so one can take V3 in the developing algebra. So this is one thing, and then another thing is you can do is take the symmetric square of V2, and they come with two coefficients. And so these coefficients are also not independent. So so let me call them C2 and C3. And so we have some relation. Well, I mean, oh, I'm sorry. Yeah, I wanted to say V2 here, not V1. So this is two-dimensional representation. So there is some relation between them, but we can rescale so actually, so maybe I should so I can put here some C2, which is because I already fixed the normalization of V2, this is a new parameter. And then for V3, since so there is a fixed normalization because it's a Lie algebra, my Lie algebra. So there is some C3, V3, and there is some relation between them. So I'm not, I will write down what these are. So I'm not going to write down this relation, but I will so basically there is so this is the most general deformation. Okay, so let me maybe write down the formulas that we have in the paper so that so we use some particular normalization, and in this case we have parameters S1, S2, and so this is minus S1 over 2. This is 15 S1, and this is 7 S2, and this is so actually maybe I should say, okay, so there is a V3, but there is also V1 times V3. And so the coefficient of V3 is 90 S1, and the coefficient of V1 times V3 is 42 S2. So this turns out to be the relationship between parameters for appropriate normalizations of things. Well, and sorry, this is just ordinary sums. I mean, you can write it explicitly in terms of elements, but that's more messy. And then, but there is a scaling symmetry. So here there are like, well, you can think of this case, since it's a central element, you can think of it, so we got a 2-parameter deformation, but you think of this as a third parameter because it's a central element, and in effect it's going to be this rank parameter nu that I defined before. And there is a scaling symmetry, which basically says that the only essential parameters, there are 2, which are S1 star, which is S1 times k squared, and S2 star equals to S2 times k cubed. And in this case, the relationship, so this is the algebra, this is our theorem, this is our yk nu with S1 star equals to k squared plus k plus 1 times nu squared minus k plus 1 nu cubed, and S2 squared, S2 star equals to k plus 1 nu cubed. So this is how it works, and this shows. So if you consider so if you take S1 star plus S2 star squared over S1 star squared and call this U, and then take zeta equals to k inverse plus k plus 1, then you get a cubic equation. Zeta cubed minus u zeta plus u equal to 0. And then so there is a Galois symmetry over the field C of u, which acts. So this is the group S3. So it's a Galois group of this equation. Namely, so this C of zeta containing C of u is a cubic extension, which is not normal, not Galois. And but so we need to make another quadratic extension to make it Galois, and that would be C of k. So this is the splitting so this is the splitting field. And so what we get is that so we have this S3 symmetry, and so the way it acts is so there are two generators of this S3. So there is 1, 2 acting on S1, 2 acting on k comma nu is minus k minus 1 comma nu. So this symmetry is classical. We already see it in Calogero-Moser system. So nu is just the number of particles, and k is a parameter. But remember, in Calogero-Moser Hamiltonian, the coupling constant is k times k plus 1. So k goes to minus k minus 1 is a classical symmetry. But the second symmetry, sending k nu, you can check that it's sent it to 1 over k times k nu. And this symmetry you do not see so easily at the level of Calogero-Moser system. So actually you can see it. There is some work of Enriquez and myself in Calak, where there are some relationships between Cherednik algebras of different ranks, which indicate this symmetry. But it's a less, and it's also seen in the theory of McDonald polynomials, but it's a less obvious one. And so this is this triality, which physicists use a lot. So so for toroidal algebras, well, they have these parameters Q1, Q2, Q3, whose product is 1, and there is a group S3 acting on them, and that's exactly this group. This is the rational limit of this group. So, so any questions about this?
So I actually have a question. I'm not sure if I fully understood how you constrain the parameters in the deformation. Did you impose Jacobi identity or something like that? Or what exactly? How do you get the numbers?
That's right. Okay, so we did this was done by computer. So indeed, there is a Jacobi identity. So what you want is you want your deformation to be flat. So you don't want the algebra to collapse. And this imposes some kind of Jacobi identity, which is messy but can be easily written by computer. And so if you write it with undetermined coefficients, so if you look at the deformations, all possible deformations that are kind of degree filtration preserving, there is more parameters. But this identity imposes some equations on them, and what you are left with is this locus.
Okay, thank you.
Mm-hmm. But this coincides with what exists in physics literature, in particular, I think, in your work, right? Is this similar?
Yeah, it is. Yeah.
Mm-hmm.
Okay, so why it is that the parameter nu, which arose as a large n limit, as what you get in the limit of large n, is a classical parameter in these algebras that are familiar to us. Does somebody can explain this?
Well, I mean,
what is the finite n story relative to the large n one that appears in?
So the finite n story. So okay, so the point is that we have this y k nu, and if so, if nu is an integer, n is an integer, then there is some ideal I such that this is equal to the spherical Cherednik algebra E H can E, and this is a certain ideal. So actually, there are many ideals. So for generic values of k and nu, this algebra yk nu has no non-trivial ideal. So it's going to be a simple algebra. But for special values, so if you draw the plane, k nu plane, there are many different lines and curves there, which on which there are some ideals. And actually, there are ideals. So I learned from David Gaiotta recently that there are ideals which depend on 3 integer parameters and which correspond to some kind of deformed Kalinov-Moser systems with 3 integer parameters, with 3 groups of variables, n1, n2, and n3. Miroslav, I think it was in his work, was it with you?
Yeah, I can actually comment on that. That might be helpful for Mina. So you should think about n as a number of M2 branes along one of the C's inside C3 in omega deformation, and the different n1, n2, and n3 that Pavel is mentioning correspond to just more general configuration of intersecting M2 branes. And these algebras that Pavel is talking about, these quotients by those ideals just correspond to these different Coulomb branch algebras associated to these intersecting M2 branes.
That's right. And so the simplest case is when n1 and n2, so n1 is n, but n2 and n3 are 0. And in this case, you get what I just wrote here. And this, you can use this to interpolate and get this continuous family. But once you have that continuous family, you already have other ideals which have this n1 and n2, and or n1 and n2 and n3. So I knew about the ideals with n1 and n2, but I did not know about n1, n2, and n3. And what is more interesting, that Oleg Chalik, who is an expert in these systems and basically developed the theory of these deformed Kalinov-Moser systems, he also did not know about n1, n2, and n3 ideals.
Okay, I'm still missing something, but maybe it's fine. The thing I'm missing is that usually Q1, Q2, and Q3 do not get related to the number of M2 branes. I guess that's what somehow that's not connecting in my head. But okay. So for the I imagine that there is an analogous story for the quantum toroidal algebra, right?
Exactly. That's where you appear. So this Q1, Q2, Q3 appear. And then there are special, again, for generic values of those parameters, there won't be any ideals. But when these variables are special, for example, when one of the Q's is an integer power of another, or maybe a rational power of another, there will be some ideals. And that should be, so that integer power should be, I don't know if this can be interpreted as a number of branes or things like that, but that's the toroidal version of what I was saying.
Do you understand this? Does Miroslav understand the physics of this? Because this is new to me. I think it's very interesting, but it's.
I'm not sure what exactly physics of what exactly you mean. Let me first comment on your concern about like Q not having any. So there are two things. There's an orientation of the branes, and the orientation of branes is captured in the parameter nu, and there are the Q's corresponding to the parameter epsilons, the omega deformation parameters. And by getting differentiality images of the systems, you can do two kind of things that are kind of opposite to each other. You can either change the support of the M2 brane or permute Q's.
Okay.
So I think that was the only confusion you had. You can do one of those things.
No, that I understand perfectly well. The thing I don't understand is usually in my world, the number of M2 branes has nothing to do with Q1, Q2, and Q3. Q1, Q2, and Q3 are geometric, and the number of M2 branes is something completely different, which one can choose independently.
Yes, I agree.
The fact that he's relating them is surprising to me. So I try to understand it, and I'm still not understanding it. But we can go on.
Yeah.
So these Q's are become so they are variables when you get this thing from equivariant K theory of some kind of Hilbert schemes, right? So if you do equivariant K theories, then initially they're just variables. But then, so these effects, when you have these ideals, this occurs at special values when the Q's become dependent on each other.
Okay.
Like one
Okay.
is a power of an integer power of another.
I
They are
think
all
such,
integer powers of each other, like rational powers of each other.
I think such phenomena are going to be extremely, extremely interesting. So this is really interesting.
Right. So the most interesting
Understanding what happens
phenomena.
with special values of Q. Very.
So the most interesting phenomena here occur when both K and mu are rational. And this is where you see those ideals with 3 integer parameters. And all of that story is going to extend to this toroidal setting with an extra piece of fun, which is that also you can allow Q to be root of unity. And then there will be some extra resonances, which you don't see in the rational world unless you go to characteristic P, which physicists don't like to do. So
Are you going to tell us about this?
No, I don't know anything about this actually. So this has to be studied. In fact, I didn't even know about the 3 parameter family of ideals. So I really need to understand that better. I only learned about it like a month ago or so, maybe several months ago. Yeah.
Very good.
No, now what I want to do is I want to explain how to talk about these Youngians from the point of view of Deligne. So I don't know. Is it okay? You said that I could still talk a little for some time, yes? Or
Yeah, sure, absolutely. There's no constraint.
Our talks are usually at least 2 hours long.
so at least 2 hours? Okay, yeah. So this now I'm afraid it will be a bit. It's a completely different kind of math. So, but it's very useful. And some physicists, for example, Slava Ryczkov, who does basically the statistical mechanics models, already fell in love with them. So so maybe I should tell. I should advertise them to physicists. That they're very useful. So this is a machine which allows you to make n a continuous parameter. In very general kind of settings, in any problem involving classical groups. And by classical groups, I mean symmetric group, but also GLN, ON, SPN. And therefore, for example, if you have supergroup GLMN, that also applies because it contains such groups and so on. Anything that's built that contains in it one of those groups can be interpolated to complex values of n using this machine. And so that's what it is. So let me explain first where it came from. So there is this notion of symmetry. So if you have a group or supergroup, so G is a group or supergroup, then you can consider the category of finite dimensional representations of G. So category of finite dimensional representations. And what kind of a category is this? So first of all, it's a category which is linear over your field. So in this case, complex numbers, which means that all homomorphisms of representations vector space over C, and and moreover, this is what is called Artinian category. So what does it mean? This, first of all, means it's an abelian category, which means that you can take, do the normal things you can do in representation theory, which means that you can look at kernel image of homomorphism of representations, co-kernel. So you can consider exact sequences, complexes, and so on. Exact complexes and so on. So this is what it means basically to be abelian. So basically it looks like category of modules over some ring. Then roughly speaking, subcategory of modules of some ring. Then also Artinian means that it's has some finiteness conditions. So so Hom spaces are finite dimensional, and objects have finite length. So this means that you can have a, so every representation has a finite composition series such that successive quotients are irreducible representations. Not necessarily direct, for example, if you have you know, groups which are not compact or supergroups, it's not necessarily true that representations are unitary or completely reducible, but you can always write a composition series such that successive quotients are irreducible and the length is finite. So this is a, and then it also has monoidal structure, which means that you have tensor product of representations and you have associativity isomorphisms. Then it's also rigid, which means that you have the duality. And then you have, it's also symmetric, which means that you have a symmetric braiding. And if you apply it twice, you get the identity. And then there is a, so this is a, tells us about the additive structure of this category. And this is a multiplicative structure. And then there is an axiom of connection between additive and multiplicative structure. And this is just that the tensor product is bilinear. So if you tensor two morphisms, F and G, this is a bilinear map. And there is a axiom which is that endomorphism of the unit equals to C. Well, this is a very, it's not a very important axiom, because if you don't impose it, all you will get is just a direct sum of several copies of several categories of this. And categories of this type are called, so such categories are called symmetric tensor categories. We'll call them just STC. And the question is, to what extent they are more general than just representation categories. And so this question was asked and answered by Deligne. And so it turns out that there are that they are more general than representation categories. But if you impose one extra condition, then it's exactly the same as representation categories. So Deligne introduced the notion of moderate growth. So this is a condition. So symmetric tensor category C has moderate growth if the following thing is true. So for every object X, there exists a positive number Cx, actually greater or equal to 1, such that the length of X to the n is less than or equal than Cx to the n. So length means length of composition Cx. So you should think of it, for example, a lot of the time these categories are semi-simple. In this case, this is just a direct sum of irreducible objects, and you count how many summands you have, and that number should not grow faster than exponential. So actually, it's in computer science, this is regarded as a fast growth, exponential growth. But in the theory of tensor categories, this is the best you can hope for. And if that happens, this is called moderate growth. And then there is a big theorem of Deligne, which he proved 20 years ago, and it says that a symmetric tensor category of moderate growth is of the form rep G for G as supergroup. Well, I have to be more precise what I mean by rep G. So this is representation. So you have to so more precisely. So we have some element Z in the even part of the supergroup, which squares to 1, and conjugation by this is the parity automorphism. So this is called parity element. You have to fix a parity element in your supergroup, and then you should look at representations of G, Z, which means representations of G on superspaces so that Z acts by parity. But this is a kind of minor point. Essentially, it's representations of G. So a moderate growth category is always of this form, and G is uniquely determined. So in fact, this G and Z are uniquely determined. So we don't get any surprises if we impose this condition of moderate growth. But without moderate growth, this is not true. And there are some new categories. And what we have, well, it's not known, classification is not known, but in particular, what is known is that there are interpolations of rep G. And these are exactly what these Deligne categories are. And so let me describe what they are. So let me first describe how to interpolate representation theory of GLN. So this is going to be rep GL, let me call it GL new. And this is interpolation of representation theory of the general linear group of C. So before that, any questions? All right. So so the goal of this, so I want to build. So this category is already present in the paper of Deligne and Milne on Tanakian categories. (1981), and there it appears as a counterexample to this theorem, which wasn't known at the time. But without the moderate growth condition, it's false, and that was a counterexample. But later, Deligne realized that those categories are interesting by themselves, and other people also realized and studied them. So now there are a lot of papers about them, and even some applications to physics, as I mentioned. So how can we interpolate the category of representations of GLN? So this is finite dimensional representations. Well, since matrices of non-integer size are not easy to define, to interpolate, we really need to describe this category in a way that is not going to mention matrices. So we need to to define representation category of GLNC in a way that doesn't mention matrices. And desirably, so N, the problem with rep GLN is that N is an size of matrices, so it has to be an integer, but we want to describe it in such a way that it will depend on N as a parameter, and then we will be able to interpret. And so for this purpose, what one does is, so for this purpose, we will use the following fact. So if V equals to Cn, so we gradually will get rid of the matrices. But so far, we have to start with matrices. So we have matrices act on vectors, which is Cn. And then we have the dual representation. And any irreducible representation is a direct summand in a V to the K, V star to the M, where K and M are some integers. So this is known since Hermann Weyl. So therefore we can do the following thing. So we can take this object, I will call it Km, which is V to the K times V dual to the M. And then I consider the category C is the category consisting of those objects Km. And then rep GLN is what is called the Karoubian closure of these categories, which is a general procedure that you can make with any additive category, which means we first of all adjoin images of projectors. So this means that if you have a map P x to x such that P square is P, then add object image of P. Because this category is not abelian, it doesn't have images and kernels of morphisms, but we are going to formally adjoin images of projections. So it turns out that it's not easy to adjoin images of morphisms such that it preserves tensor products and so on. But for projectors, it's okay. And then, so this is called idempotent completion. And this can be done for any category whatsoever, even without any additive structure. And the second is that we add finite direct sums. So by adding idempotent images, we will find all the irreducibles because they are direct summands in our tensor product. And then when we add finite direct sums, we will get arbitrary representations, which are direct sums of irreducibles. Because any representation of GLN is completely reducible. It's a direct sum of irreducible representations. Okay, so that means that we only have to describe this category in a way that doesn't mention matrices. But so far, certainly, the description we have is still mentions matrices because we say that it's V to the K times V star to the M, and we look at all the maps that are GLV invariant. But then the point is that you can write that down using diagrams, and that description already is going to be good from that point of view. So any questions?
How do the projectors act? Like, what is?
Well, suppose we have this V to the M times V star to the K. Or it was the other way. V to the K, V star to the M. And suppose you have a direct summand, some W. So this means that this is really W plus complement. Okay. So then there is a projector So if I call this object X, so projector from X, which is W.
I see, I understand. Okay.
So P on W is 1 and P on W perp is 0. And then image of this projector is this W. And this projector is invariant with respect to GLM. So other questions? By the way, do you usually make a break? Because I've been talking for hour and a half already, and is anybody tired?
I think it's okay if you finish the story.
Okay, I'll finish the story. All right, so okay, so then I have to describe this category C, and so so this category C is so how do we write? So we have to describe homes, right? Because we know the object. So what is home from KM to PQ? Well, so this is the same as home over GLN of V to the K, V dual to the M, V to the P, V dual to the Q. And so you can rewrite that by moving all the V's to the left and all the V duals to the right. So this is going to be home over GLN from V to the K plus Q, V to the M plus P. And this is so this is going to be 0 if K plus Q is not equal to M plus P, which is equivalent to saying K minus M is not equal to P minus Q. But otherwise, we have sure while duality. So we know that home over GLN V to the N V to the N is generated by the group algebra of the symmetric group. Well, and it coincides if this N is less than or equal than capital. And we are going to take large capital N limits, so that's okay. So so this is sure while duality. And and then we can draw this as pictures. So how should we draw it? So if you view this, so we'll have this map from V to the K times V star to the N. So let's say, so there's going to be V to the K. So I'm going to have K copies of V. And then I'm going to have M copies of V star. And here I'm going to have P copies of V and Q copies of V star. And so what I'm going to get is, so I'm going to draw arrows like this. So these are going to be down arrows for V and up arrows for V star. So there are down arrows for V, up arrows for V star, down arrows for V, up arrows for V star. And then I need to connect them in such a way that orientations are preserved and all the arrows are used. So so that's going to be a basis of for large N. It's going to be a basis of morphisms. So let me just take an example. Let's say home from V cubed, V star squared to V to the fourth, V star cubed. So the balancing condition is satisfied in this case. And so what I get is I get 3 down arrows here on the top and 2 up arrows. And here on the bottom, I've got 4 down arrows and 3 up arrows. And I can draw, like I can put a wall between them so that we can distinguish them. And then I have to connect preserving orientations. So something like this. And I don't keep track of the intersection. So since I'm doing usual GLN and not quantum GLN, I will not distinguish between upper and overcrossings and undercrossings. If I did, well, this has a quantum analog, and then I should distinguish between overcrossing and undercrossings and use scaling relations. So let's say I do this. Let's say I do this, and let's say I do this and this, and everything should be connected. So since balancing condition is satisfied, it should be possible, and there should be n factorial ways of doing that. And then, so these are morphisms. And so I'm going to look at the case of large n. So they're going to be independent. And then composition of morphisms is the concatenation of pictures. So if I have another picture of this sort, so for example, let's say I have a picture here. And let's say it goes to 2, 1. Okay, so that means, so let me say I'm going to do this, and I'm going to do this, and I'm going to do this, and let's say this. Okay, so then I need to concatenate, and so concatenation is just this here. And I get a new picture. So I can forget about these middle arrows, and I get a new picture. But the only difference is that now I have closed loops. So I have 2 closed loops. And that wasn't allowed. So this is not a picture of the kind I had before. However, I can compute what this is in my category of representation. So closed loop just means that I take the trace of the identity operator on the space V, and that computes dimension of V. So this means that I can remove the loops, and then I can replace each loop by a factor of n. So, so therefore, what I'll get, let's see, I have 3 arrows here, 2 arrows here, and I have 2 arrows here, and 1 arrow here, wall. So the wall is drawn because any line that doesn't intersect the wall has to go from top to bottom, and any line that intersects the wall turns around. So, so if I remove those loops, what am I left with? So these 2 are switch order. So get, say, this way, and then this thing goes around to here, right? And this thing just goes this way. So this is the picture is left when I take this, but then there is a factor n squared times this. So this is the rule of composition of morphisms. And so, well, I didn't quite describe my category because, as I said, for finite n, these pictures are not independent. But in the limit, when n goes to infinity, I described it in a way that is doesn't mention matrices and in which n occurs as an analytic parameter. So now I can define the category rep GL new tilde with objects KM and morphisms as above. So the morphisms do not depend, morphism spaces do not depend on nu, they're just pictures. linear combinations of pictures, and composition also as above, with n replaced by complex parameter. So that's a category, and then we define rep GL new. So this is the main definition. Is a Karoubian closure of rep tilde GL. So this means that I add images of idempotence and add finite direct sums. And so to understand what we get in this way, we should look at the endomorphisms of this object Km. Well, this is, as we know, just the group algebra of symmetric group K plus M, but with a different multiplication. Because we turned around M of the K plus M inputs. And this multiplication depends on this new, because when we get loops, I mean, when we compose ordinary permutations, we never get loops. But here we get loops, and then we have to replace them with new. And so this algebra depends on new. And this is called the Wald-Brouwer algebra. B K M of new. So let me give an example of what this algebra looks like. So for example, what is B11 of new? So B11 of new means that we have, why is it called Wald? Because we had this purple wall here everywhere. And so in the case of B11, we have so we have down arrow and up arrow, and so we have two elements. So we have so two-dimensional algebra. So we have this element, which is just one, but also we have this element, which I could call A. And then what are the relations? So if I take A squared, that's going to be basically this thing, and I have to remove the loop. So this is going to be nu times A. So this means that this algebra BKM of nu is polynomials in A modulo the relation that A squared equals to nu times A. And what we notice is that this algebra is semi-simple if nu is different from 0, and not so nu equals 0. So it does depend on nu, and it's semi-simple in this way. And that there is a general theorem, which is much more non-trivial, but can be proved and is known, is that B Km of nu are semi-simple for all K and M, if and only if nu does not belong to Z. So, and the corollary of this is going to be that, well, this will mean that when we, since it's a semi-simple algebra, this will mean that if endomorphism algebra is semi-simple, then this will mean that object Km decomposes in a direct sum of irreducibles. So this means that we will have a category where we have complete reducibility. So it's a semi-simple category. So this rep GL nu, for nu does not belong to Z, is a semi-simple symmetric tensor category. And it doesn't have moderate growth. So it's pretty easy to see it. So no moderate growth. Because if
Can you say again what semi-simple means in this context?
So this just means that every object is a direct sum of simple objects, not just an extension, but a direct sum of simple objects. And there is no moderate growth, because if I take, for example, v to the n, then it is going to be a direct sum over partitions, the lambda parts, and okay, so first of all, length of every object. So it's clear that the number of summons in every object is at most so does not exceed square root of the endomorphism dimension of the endomorphism algebra. So if you have x, which is a sum of ni xi, and these are simple, and ni are integers, then hom from x to x is the direct sum of matrix algebras ni. So dimension of hom xx is the sum of ni squared, and the length of x is just the sum of ni. So length of x is always at least the square root of dimension of hom of xx, because the sum of ni squared is at least the sum of ni squared. And so if you take x equal v to the n in this category, then hom from x to x is the group algebra of Sn. So we know that in the usual case, it's the quotient of the group algebra. It's only the group algebra if the dimension of V is sufficiently big. But here the dimension has essentially been sent to infinity. So this is going to be true for all n. And so this means that the length of V to the n is at least the square root of the dimension of this, which is n factorial. And this is bigger than a constant to the n for any constant for sufficiently large n. So this means that there is no moderate growth here. So this is the category you get. So how is it related to the usual category? So what happens when nu is in Z? Let's say in Z greater or equal to 0. Something very similar happens when nu is negative and integer. So in this case, this category is not rep GL nu, is not semi-simple, and it's not abelian. But you can embed it into an abelian category. And another thing you can do is it has a tensor ideal. So of some negligible morphisms. Such that if you take representations, the GL nu modulo this tensor ideal, this is just ordinary representation category of GLN. And to distinguish them, I will call them classical. So this is going to be classical representation. So this will exactly kill some morphisms whose trace, so negligible morphisms are morphisms which you cannot detect by computing traces. So trace of such morphism composed with any other morphism is 0. So this is very similar to what you do when you construct so for example, when you construct modular tensor categories in, let's say, West-Lumina-Witten conformal field theory. So you take, if you want to construct them from quantum group, you start with quantum group at roots of unity. So you have many representations, you the tensor in a certain way and so on. But then there are some morphisms which are negligible and objects which are negligible. So they have dimension 0. So you cannot see them if you compute invariance of links, these objects. And then you have to throw them away. And when you throw them away, the number of terms in tensor product goes down, and quantum dimensions end up being less than the classical dimensions. That's what happens. And the same will happen here. So in the category rep GL nu, these dimensions are essentially infinite because we don't have moderate growth. But when we take a quotient, they become fine. So this is how it works. And now, if you have any construction in with classical groups, you can basically interpolate it. So if you have any construction with classical GLN, you can interpolate it using this thing. So for example, you can interpolate anything like theory of representations of affine GLN, theory of representation of Youngian of GLN, whatever you want, you can interpolate to this category and you will get some interesting extension. So, and now I want to, so in particular, so this Cherednik algebra, EHK of NE, can be obtained as a quantum reduction, quantum Hamiltonian reduction from differential operators on GLN. So this is called the deformed Chandra homomorphism in my paper with Ginsburg many years ago. But really, essentially, it means the following. So this EHK of NE should be thought of as quantization. So this is a quantization of Calogero-Moser space. So this is the space of pairs of matrices X and Y, such that X, so these are n by n matrices, such that X bracket Y plus 1 has rank 1, and this is modulo GLN. So this is a quiver variety. So this is a basically space of U. So it corresponds to V being n-dimensional. It's a Nakajima quiver variety. V is n-dimensional. W is one-dimensional. And then so basically you have this this kind of quiver, Jordan quiver. So this is really a GHM quiver. So this corresponds to instantons. And on the four space, and so this is this is diffeomorphic to the Hilbert scheme of C2. So this is a hyperkähler manifold, and if you take in one of the complex structure, it's a Hilbert scheme, then the other complex structure, it's this Calogero-Moser space, which is an affine variety, and this Cherednik algebra is a quantization of this. So this means that it's when I set that parameter t, which I said was the Planck constant, to 0, that's what I will get. And so this variety is obtained because it's a quiver variety. So this is Nakajima variety. So this is a reduction, by definition, a reduction from space of representations of the doubled quiver. So representations of the doubled of this quiver, which is this quiver here. And this is a symplectic space, so the quantization will be I have to take differential operators on representations of Q, which is really GLN cross Cn, and then we do quantum Hamiltonian reduction appropriately. And so this procedure can be, we can interpolate this. Because it's a purely algebraic procedure, we can interpolate this in rep GL nu, and then we will get this Yangian K nu. So that's one way of getting it, and this is really the way that is described in Costello's paper. So where he constructed basically, but he doesn't use this language, but what he does is he interpolates this Hamiltonian reduction procedure. But then you can also get it from, I mentioned that, so this is one construction of this Yangian from Deligne categories GL nu. But actually, I mentioned that also for symmetric groups, you can define those Deligne categories. And one can also obtain the same algebra from S nu. And so this, and that also extends, well, modulo some things have not been. So this was, this is already done by my graduate student Kalinov. There are some details missing, but basically the same procedure works for matrix versions when you take deformation of GLN of GLN tensored with polynomials in two variables. So now I want to stop for questions, and last thing I want to do is explain what happens, what is the Deligne category for symmetric groups, and how to interpolate the Cherednik algebras, actually full, not just spherical, to get this Yangian. So this should take another maybe 10 minutes. So are there any questions up to this point?
Yes, I have a quick question. So you mentioned that this works also for quantum groups.
You can make that work for quantum groups, yes.
So this gives you a way of computing Homfly polynomial for I haven't
Absolutely.
seen such an approach.
Yeah, absolutely. You can compute Homfly polynomial. So let me mention that. So that's a very good question. So so can define in the same way rep Q GLT GL nu, and this will depend on parameters Q and A, which is Q to the nu, and this is going to be a braided tensor category, which is semi-simple if nu well and Q are generic. So defined in the same way. You still have those pictures, but then you should have you should distinguish between upper and overcrossings and undercrossings, and you should impose the Homfly-Skene relation.
Does this extend to roots of unity as well? Like quantum groups that roots of unity?
You can do that too, but that takes a little bit more. So the problem is whenever you have a non-semi-simple category, what you will have is, so when you define this category of pictures, it will not be abelian. And then, well, either you have to kill some ideal, and then we will descend to some kind of finite dimensional category usually, or maybe not, some intermediate category, or you have to make an abelian envelope. That's a very non-trivial procedure. So there is a machine that allows you to avoid this procedure, which comes from model theory, which is called the ultra product limit. And then you can define these categories, but then it is this ultra product limit is a kind of non-constructive guy. So you take it, so you can always take it, but it is difficult to compute what you get. But yes, you can define things at roots of unity as well. So this is a very flexible construction. The only problem is that when you define, you can define anything you want. The problem is that it is not easy to calculate what you get. But in some cases you can. And so for roots of unity, we hope that we can compute what happens.
Interesting, because it's very interesting because Transformers theory at large N, well, at least physicists thought that such a thing, in general does not exist on general three manifolds. But if, or at least that it's going to give you something very, very singular and pretty terrible.
Yeah, but for general three manifolds, you need to define invariance of three manifolds. You need a fully extended three-dimensional TQFT, which means that should give you numbers for three-dimensional manifolds. And for that, you need the category to be finite. It should have finite number.
I thought all I need is quantum groups of roots of unity. No, I need something more.
That's right. Quantum groups of roots of unity will give you that, but they have finitely many objects. So when you go to the limit, it will not finiteness. So finiteness is not preserved under these limits. So we'll have infinitely many objects, and you will get infinite sums. So this will not make sense as a number.
Oh.
No, but this is a braided tensor category, and the Reshetikhin-Turaev invariant of links, you can still define invariance of links, is exactly on the nose the Homfly polynomial of Q and A. And when A is an integer power of Q, this category develops an ideal. The quotient is the classical representation theory of the quantum group, and then you get evaluation of Homfly polynomial at A equals Q to the N, which you can get from representation theory of quantum GLN.
So is this something that's well known? It's in the literature, or?
It is, yeah, but it has a different name. So this is called the Skene category. There is a paper by Christian Blanchet, I think, from 20 years ago, which describes this. Right, Kolya, is this correct?
Yeah, that's a long story. Yes, it goes back to the 90s.
Yes.
Actually, Turaev, I think he kind of gave a first example for the torus of such category. Yeah,
Yes.
yeah, it goes back to these people.
Yes. Okay. Right. But again, whenever you have any kind of construction involving quantum GLN, you can interpolate it using these categories. And in particular, if you do the same thing as in Costello's paper for this quantum GLN, so quantum reduction from the Q, quantum differential operators, Q differential operators, you will get, in the finite situation, you will get double affine Hecke algebras, and in the limit, you will get quantum toroidal algebras. Okay, but now I want to explain the story about symmetric group, but are there any questions?
So yeah, actually, so the part with rep-Q, it's clear how to generalize, but in the first part of your talk, you kind of given a presentation for the algebra of Weiss as a universal enveloping algebra or something. So in the case, in the difference operators case, is there an analog of that?
Yes, it will be enveloping, still universal enveloping algebra, but of the quantum torus.
Okay.
Xy equals to QYX.
So one can in principle ask the same questions about the flat deformations and so on.
Exactly, yeah, but because we don't have a filtration of this sort, so this is not going to be filtered deformation. Things change, so you have to compute some kind of Hochschild homology. I don't know the answer to that, but I expect that if you set up the problem correctly, you will show that there exists only one deformation. And in some sense, Costello solves that problem. So he considers deformations not, he considers kind of, he does not try to deform one single algebra, but he deforms a kind of tower of algebras. And then he shows that there exists a unique deformation because that can be expressed in terms of cyclic homology, which you can calculate.
So universal deformation in a sense is calculated.
Well, if you define it in a suitable way, then you can reduce the calculation to cyclic homology, and So Costella does it in his paper for Jungians, and I think the same story will work in this setting as well.
Thank you.
Okay, other questions? So let me try to go quickly over this last thing. So this, I want to define the category rep S nu. So again, we need to write rep Sn without mentioning permutations. And in this case, instead of representation V, which generates our category, we will use representation P, which is just Cn. So this is the permutation representation. And this is self-dual now. So this is actually not just a representation, it's an algebra. So multiplication is invariant with respect to symmetric groups. So it's just functions on the set of n elements. And then any irreducible representation is a direct summand in P to the n. So so again, we can define the category of objects.
Pasha, but by self-duality, you mean as an S module?
As a, yeah, as an SN module. So I can look at the representations P to the n. So I will call this representation n. So now it has a unique index n. And then I can look at this home from n from k to p for large n. Actually, I shouldn't use n because n is my symmetric group. Actually, probably I should use capital N for symmetric group because physicists always denote large integer by capital N. So yeah. Wait, no, this I don't want to change, sorry. Okay, so for large capital N. And so this is just the home over Sn from P to the N, K to P to the P, which is the same, of course, as home over Sn from C to P to the K plus P. So all I need to compute is, I need to compute, so this is invariance. And so this is really, what is it? It is functions on one n to the power r, Sn, where r is this k plus p. And so we have a basis of orbits, basis corresponding to Sn orbits. And what are Sn orbits? So Sn orbits on what? On elements of the set. So they are vectors x1, xr, where xi are elements from one, numbers from 1 to n. And what are the orbits? So orbits are, so let me call orbit O. So these orbits O correspond to equality patterns. So basically, we have elements of the set x1 through xr, and we're allowed to relabel them. But of course, the only thing that's left, if you have a bunch of elements of the set and you're allowed to relabel, is which elements are equal and which are not equal. So this is what I call equality pattern. So for example, we can have equality pattern O, where, so this is vectors x1, x2, x3, x4, x5, where x1 is equal to x3 and x2 is equal to x5. And I don't say anything about the other. elements. So the other elements should not be equal. So no other equalities. There are orbits like that, and this corresponds. So if I draw a picture, like I have my element, so x1 is equal to x3, and x2 is equal to x5, and then there is a x4 which is on its own. And so what this is it's a set partition. This is called a set partition. So I partition my set of 1R of entries of this vector into subsets according to the equality pattern, which are level sets of my function. And so we see that, but of course, so what arises is set partitions into at most n subsets, because they are partitioned according, these are level sets of my function, so I can only have n capital values. But if n is large, then all set partitions occur. And that therefore what we get is that home from K to, let's say, P is, let me call it P, K plus P, which are set partitions, C of P, K plus P, set partitions of the set 1 up to K plus P. By the way, the number of set partitions grows very fast. It is a so-called Bell number, and grow super exponentially. So this shows that the category we will get at the end will not have polynomial growth, not have moderate growth, which is not surprising in view of Deligne theorem. Now. So this is like that, and then how to multiply, how to compose. Well, again, we can draw pictures. So let's say we have some morphism from x to the k to x to the l, and then from x to the m, say f, g. And so how do I compose? So I have k. So let's say I have 4, 3, and 5. Sorry, I should write just this. 4, 3, 5. Okay, so then I have to put dots, right? So now I don't have arrows, just dots. So there are 4 dots on this level, and there are 3 dots on this level, and there are 5 dots here. And then I have a morphism here. So morphism here is a set partition. So I should partition the first 2 rows into subsets. Somehow. So let me do it this way. Say like this, and like this, and like this. Okay. And then I have to partition the second morphism. So this is going to be my morphism G, or F, sorry. And then there is a morphism G, which I will draw in purple, which will be a set partition of the second and third row. So let's say we will have like this, like this. Okay. And so when I compose this, what am I supposed to do? Is I'm supposed to kill the middle row and just keep the oh, okay, so I should say that what I want, I'm going to compose morphisms. So for every O, I have this indicator function delta O. And then I will, but this basis is not very convenient to multiply. I will get too complicated expressions. So I will replace it with epsilon O, which is the sum of delta O over all O prime subordinate to O. And this means that all equality patterns. So this epsilon O is means that my equality pattern is non-strict. So non-strict equality pattern. So this means that I do not require, when I define delta O, I require that whatever elements I did not say were equal are not equal. But epsilon O means that they may or may not be equal. So this means that it's a triangular change of basis. And when I multiply, and I denote this by such pictures, so it's a non-strict equality pattern. The elements which are in the same blob have to be equal, but the elements that are in different blobs might also be equal or might not. And so when I compose, I'm supposed to draw the corresponding equality pattern just for the first and third row. So for example, if this is equal, if this thing here is equal to this thing here, and this thing here is equal to this and to this, then all of them are equal. And so what I get at the bottom, so at the bottom I will have 4 things on the top and 5 things on the bottom. So all of these are equal. So this means that basically I have the last dot here is equal. So I forget about the middle. So is equal to the middle dot here. So then I get this. And then this thing that I had here will remain. And then this thing here will remain. And this thing here will remain. And this thing here will remain. But then there is this thing in the middle, which is this thing here, which I forgot, but it could be anything. So this means that I will get a coefficient, which is the number of choices for that. And that's exactly my number n. So this is going to be n times this. So again, we got a polynomial multiplication law, in fact, a monomial one as before, and it's obtained in this way, that I delete so I put the pattern that follows from these 2 patterns, and I delete the middle row, and then whenever I delete a component which is entirely contained in the middle row, I have to put a factor of n. Does it make sense?
Yes, it does. It's wonderful. Yeah.
Okay, and so and now I can define this category C tilde, and then I take rep S new. So tilde is the category defined so with n replaced by new, and then I take rep S new, which is the Karoubian completion. And then, so again, to understand the structure, I should consider endomorphisms of P of K, and so this is called the algebra par K. So this K is partition algebra. So basis is the set partitions of the set of 2K elements, and some funny multiplication. And there is a theorem. So this depends on the parameter nu. And there is a theorem that people proved. I think probably Halverson and Ram, that this is semi-simple if and only if nu does not equal to 0, 1, 2, and so on. So here only positive integers are bad and negative integers are okay. And this implies that if nu is not equal to 0, 1, 2, and so on, then this category is a semi-simple symmetric tensor category. And if nu is equal to 0, 1, 2, and so on, then rep S nu contains some ideal I, and the quotient is a classical representation theory of symmetry group. So nu equal n, capital N. And maybe I should make a remark what the simple objects look like. So I did not say that remark. So for GL nu, simple objects, so it's like irreducible representations, they are labeled by pairs of partitions of anything. So this interpolates irreducible representation of GLN with highest weight lambda 1, lambda k, and then many zeros, and then minus mu k, minus mu l, minus mu 1. And this whole length is capital N. So if you have any two partitions, then for large enough n capital, you can form a weight for GLN, which is this kind of sequence, and you can consider it a representation of that weight, and this interpolates to V lambda mu. And for S nu, so the simples are X lambda for one partition lambda, but of anything again. And this interpolates the following partition, n minus size of lambda, lambda 1, lambda 2, lambda k. So it's irreducible representation of Sn for this partition. So in other words, we have to take our partition, let's say, for example, lambda equals to, let's say, 3, 2, 1. So you draw the Young diagram of that, which is this. So this is our lambda. And then you have a very big integer n. So you add a very long first row of size n minus size of lambda. And this is called the n padding of lambda, because we add a pad here, so lambda tilde of n, and so this is what it interpolates. Okay, so so this is what this category looks like, and now so you can define the algebra HC of n. Like I said, that anything containing symmetric group can now be interpolated. So in particular, H, the category of modules over this Cherednik algebra. So probably the talk has been too long, so I'm not going to write a definition, but in principle, but you can write down the definition of Cherednik algebra in such a way that you will not use elements. So we say it categorically friendly way, and then so this will be a category. So roughly speaking, it means the following thing. It's a category of M in rep. So H. So we put nu here, which is an arbitrary complex number. So this is M as rep S nu. And now we have to add to it action of x's and y's. And x's, they change in the permutation representation, and y's also change in permutation representation. So we have to have, this means we have to have a morphism in this category from P to M to M. And we have another morphism from P to M to M. And then you can write relations appropriately. This is 0, this is 0. And then it takes some work to write this relation. interpret what you have in categorical terms, but you can do that. And then, classically, if you want to define the spherical subalgebra, hk of nu e, then this is just endomorphisms over hk of nu hk nu e. And so all we have to do is we have to interpolate this. And this can be done very easily. So, so you look at endomorphisms. So this is y k nu. So classically, this is true for finite n. So e h k of n e equals to endomorphisms of h k of n h k of n e. And we interpolate that definition, and this will give you another way to define this y. And this method can be used to show, so this extends to matrix case, and Kalinov showed that this, if you define it in this way, it coincides with Costello's, with Guay's definition by real generators and relations. So Costello conjectured that his version of this Yangian coincides with Guay's. And so all we have to do now is to match up the GL nu definition and S nu definition. And this presumably can be done by a version of the deformed Chandra homomorphism story. So this has not been finished yet, but somehow there is one little thing missing for proof of that conjecture. So basically it's a nice approach to those algebras. And one nice thing about it is that for Cherednik algebra, it has a presentation by generators and relations. So you can define Verma modules, irreducible quotients, category O, all these nice objects. And if you construct Y in this way, then you construct many modules over Y by taking home from this module HE into arbitrary modules over this HK. And so from the category O, for example. And this is so this is a really nice way. So so a corollary is that if M, so if M is a H K of new module in category O, for example, then E M, which is home in S in rep S nu from the unit object to M, is a Y K nu module. And in this way, we can study these Y modules. So Y modules are very interesting. I don't think they completely understood what their characters are and what their structure is, especially at those points where we've got ideals depending on 3 integer parameters. Interesting things should happen. So this should be a very good way of studying these this representation. Okay, maybe I should stop here. Thank you very much.
Thank you. Other questions?
Pasha,
Mm-hmm.
there are also, I mean, I remember back in the early 90s, there were attempts to construct some kind of analytical continuations of categories of modules over exceptional groups, and there was the whole map of such things. So
Right.
what is known about this? I mean, is there some development?
Unfortunately, this project didn't succeed completely. So there was this Deligne exceptional series. So there
That's
were some observations that if you take a joint representation of a simple Lie algebra and take its tensor powers and do certain things there, write down various diagrams, like trivalent graphs, and so on. You will
I think
get some
Vogel was.
That's
Vogel
right.
wrote some papers on this.
That's right. So there is some kind of Vogel plane. So there are three parameters, alpha, beta, gamma, which coordinates in some projective plane, and a lot of invariants, which you can extract in this way, can be written as rational functions of those alpha, beta, gamma. So there should exist some family of categories depending on this alpha, beta, gamma, such that basically you can compute such things just from that picture. And in particular, on this plane, you can put points corresponding to all the exceptional Lie algebras, and also for classical Lie algebras, and points for classical Lie algebras, they lie on a single line. So you can just continue it, and you will get those Deligne categories. There are also lines for superalgebras and so on. And there was a hope that there is also a line for that somehow there is for every point of this category, there is of this plane, there is some nice category which would be similar to these Deligne categories. But unfortunately, it seems that when you're away from those lines corresponding to classical groups and supergroups, somehow this category is too big. So of course, the category is constructed diagrammatically. So you draw some trivalent graph and you mod out by some relations. And the space that's left seems to be too big. First of all, it's not obvious that it's not zero. And also, if it is not zero, I mean, if you put too many relations, you get zero. If you put too few relations, you will get something that's too big. And it's not clear how to construct something manageable.
So there was no progress since that. Yeah,
I guess so. So Vogel papers were never published. And basically this whole direction somehow got stuck. And in fact, it's not clear to me that there is an object here. So
no, I'm just asking. Yes.
Yes. So my guess is it got stuck because there is nothing like that. So these categories only exist for classical groups, I think, which with nice properties such as finite dimensional Hom spaces and all those nice things. So this is my impression.
Okay.
I mean, that's nevertheless very interesting. This numerics that goes with that is very interesting, nevertheless.
No,
but I don't think it rises to the level of having nice categories like this.
I agree. Yes, I mean there was some experimentation with this, but it never gave.
Yeah. So I discussed with experts such as Noah Snyder, for example, and I think he agrees with me on this.
Okay. Good. Thank you.
But so mainly the goal of this talk was to advertise the Deligne categories to physicists, and to some physicists like Slav Rychkov and his collaborators are already using them in statistical mechanics model. But this is a very good language to do large n limits where you preserve n as a continuous parameter.
Yeah, in statistical mechanics, it was kind of known. There are so-called loop models, and they analytically continue n the number of colors in the loop to arbitrary numbers since 60s maybe or 70s.
Yes, I mean the problem with this thing is that these categories are not unitary, so you cannot do this continuation in such a way that the category is unitary.
Yeah.
And so you will not get Hilbert space out of this story, but you will. But there are some non-unitary physical theories, and in those theories, such things could be very useful.
Sorry, Mina. Go ahead.
Nothing. I just wanted to say it's striking how simple it is. It's you're supposed to get gravity that way. So,
yeah, I don't know. I mean, this is more like so basically what this category are responsible. In some sense, this is a red herring, because it's just a nice way of talking about something that you can say without categories, which is that in representation theory, there are various stability patterns when certain quantities in classical group, regarding classical groups, stabilize when some parameters go to infinity. And other quantities become polynomials of this parameter. So these categories capture, anytime you have such a pattern, you can hope that it's captured by one of those categories. And many of these patterns, which combinatorially, for example, stabilization of Littlewood-Richardson coefficients, or stabilization of some multiplicities or whatever. Anytime there is something like that, there is a hope that you can explain it by using these categories. And we've been able to explain many of such stabilization patterns. So you should think of this following thing. So there is the representation theory, and this is an open set. So it's moduli space of representation theories, which is a kind of variety. And then it has compactification. So points at infinity are those Deligne categories. So more or less, that's the picture.
Okay, any further questions?
So these notes are not very ordered, but I will send them.
So in some sense, you're running, I guess, the story that Miroslav and David studied backwards, right?
Well, I mean, yeah. So the story is that there is this algebra, and I mean, it's basically the same story. So you get some kind of yeah. So you have a theory with continuous parameters, but it can be obtained as some limit. And then whenever you have a limit, you can talk about it in terms of those. I mean, well, when classical groups are involved, so we have these symmetric groups involved. And so when classical groups are involved, you can think about it as in terms of this Deligne category. So I guess you can think about if you have a brain, like in the physics language, you have n brains, then you can think of symmetric group as permuting those. But also you can think of general linear groups as acting linearly on those. So it depends on what kind of realization you want to use.
I guess I was the finite end story made sense to me always. The large and, at least to me, it wasn't clear that this is, the right story in some way, that it connects them to the finite end story the way it does. So I think now we're understanding that it really is true. So it's beautiful.
So I think the story with GL new realization, which is like in Costello's paper, is more it's more in the spirit of physics approach through gauge theory and so on. But the realization through symmetric groups and non-spherical unique algebras is kind of not so clear to me. What is the physics meaning of this? But somehow interplay between those realizations is a very useful tool of studying the representation theory of unique algebras. And I expect that looking at it both ways is quite useful also in this infinite limit.
So this connection between this, I did get a little bit tired towards the end, but the connection between the symmetric group picture and the first part is that this feels like some flavor of Schur-Weil duality, right? Like a boson fermion kind of thing. which
Yes,
should actually be familiar.
yes, it is. It's related. That's right. Yes, you can think of it this way. Yes. Well, at least. So there are two ways. So there is this interesting symmetry which I mentioned when k goes to 1 over k, after applying the symmetry, yes, you can think about this as a Schur-Weyl duality, because then that symmetry, what it does is it changes the nu. So nu gets replaced by k times nu. In Schur-Weyl duality, you don't have the same parameter. Like you have two parameters, number of factors and dimension. You don't want them to be the same. And here you have a construction from S nu, construction from GL nu, so these things are the same. But if you apply that symmetry, then one of them is going to be nu and the other going to be k times nu. So they are different. And in that setting, it is related to the Schur-Weyl duality, yes. I should mention also that there are these Youngians, so you can replace your quiver, your Jordan quiver, with an arbitrary ADE quiver, for example. Actually, any quiver, but in particular affine ADE quiver, and then you will get a story about. So it will not be Cherednik algebras, but there will be symplectic reflection algebras corresponding to finite subgroup of SL2, so Riest product groups. And such deformed double current algebras would be deformations of not Hamiltonians in the plane, but Hamiltonians on the AD singularity. And such algebras have been studied too, and they can be everything I said, except the explicit presentations can be applied to that as well. The explicit presentation, we don't have SL2 unless the group gamma is just Z mod 2, so A1 singularity. And in that case, we were also able to derive those equivariant presentations, although they are more complicated, but they're still in the same spirit. But everything else about the Deligne categories, it applies to the most general situation.
Pavel, thank you so much for a really interesting, wonderful talk. I learned a lot. That was terrific.
Okay, thank you very much.
Yeah, me.
All right.
Well, thank you very much.
Okay. Thanks for joining us.
Okay,
Thanks,
thank you
everyone.
very much. Bye-bye.
Bye-bye.